Welcome back, everybody. This is the video solution to problem 6 from the Fall 2020 Math 210 final exam. This problem is all about numerical integration. So this is a two-part problem. You see here part A, which is about using Simpson's rule and a table of values to estimate an integral. So I'm going to get right to it by writing my integral down again. And one thing as I'm writing this integral down again is I'm going to pay attention to the limits of integration, these bounds here, right? What is my domain? It's 2 to 8. Notice that in my table, it starts by giving me data values from 0 and ends with data values at t equals t. It's giving me too much data. All right, I don't need it from 0 to 10. I only need it from 2 to 8. And one very, very common mistake is for people to see all of this data and say, well, I better use all the data, and they just integrate from 0 to 10, which is not what the question is asking. So what I'm going to do is just cross out the stuff that I know I'm not going to use. So I'm only going to be using this stuff in the middle. All right, that's first thing. So let's finish copying this down. I'm going to integrate f from 2 to 8. And well, I wrote this equality here, and I mostly wrote that out of habit, right? We always write an equal sign. But when we use Simpson's rule, we are not expecting to get the actual exact value. We're only expecting to get an approximation. So instead of using equality, we want to make sure we are using the approximately equal sign. Next, there's this little constant that's going to start this whole thing off. First, you divide by 3, and then you're going to multiply by, well, the length of the intervals. So here I'm integrating from 2 to 8, and I'm going to use all these data points, which, by the way, with Simpson's rule, remember we need to have an even number, right, of intervals. 1, 2, 3, 4, 5, 6. Okay, cool. I have 6 intervals. Beautiful. All right, 6 is an even number. All right. If I didn't have an even number of intervals here, right, I can't use Simpson's rule. I'd have to choose fewer data points, right? Or go back and ask them, please give me more data points, right? I need you to just give me one more or something. Okay. And how far apart, right, is it from one number to the next? Now, if you start doing, well, let me say I'm going to take 2 and 8. I'm going to do 8 minus 2, and I'll divide by 6. Yeah, that's a formula, right? But if you write that down, it's going to annoy me. Oh, boy, is it going to annoy me. Why? Well, for theoretical purposes, it's good to know that formula, right? If you integrate from a to b and there's n intervals, you do b minus a over n. But in practice, I can see how far apart these intervals are. From 2 to 3, that's a distance of 1. Right? All of these, they're 1 away. That's what goes up here, right? This is the distance between t's. Okay, so I don't want to see b minus a over n when you're actually applying Simpson's rule to a specific type of problem. It's really going to be more useful having that formula when you're dealing with it at a more theoretical level. All right, now we're going to multiply this 1/3 factor by, well, we're going to sample the function. We're going to sample it at 2, 3, 4, etc., all through 8. So let me write that in here. 2, 3, 4, 5, 6, 7, and 8. So we're doing that sampling. All right, there's going to be some addition here, right? We're going to be adding all these values together. The last thing is we need to put in some weights. Okay, the very first and the very last get a weight of 1. Okay, usually you don't even write that in. Okay, then on the inside, right, between the ones, we have a 4, 2, 4 alternating pattern. Okay, so there's a 4, there's a 2, there's a 4, there's a 2, and there's a 4. And one thing that you should always make sure is that the very last and the very first, right, after, in between the ones, should always be a 4. It should never end with a 2, right? When you do the alternating pattern, it'll always be bookended by 4s. Okay? So there we go. We've set it up. Now, when I go to the next line, everything I'm doing here, I know the value. I can write it down explicitly. There is no more approximation. And so I really do get to write an equal sign at this level, not an approximately equal. So, okay, I have a third. F of 2 is -1. Then I have 4 times f of 3. F of 3 is -2. Then I have 2 times f of 4. That's -1. 4 times f of 5. Ooh, that's a 0. That's good. 2 times f of 6. F of 6 is 1. Okay, plus 4 times f of 7. F of 7 is 2. And then 1 times, let's see, what's f of 8? F of 8 is 3. So we just write down a 3 here. All right, and now we're just doing like easy arithmetic, right? This is -8. This is -2. This is 0. This is 2. This is 8. Okay, let's put it together. So I have 1/3 times, okay, -1 and -8 is -9. Plus -2, we get -11. Plus 0, still -11. Oh, add 2, we're back to -9. Plus 8, we're at -1. A third times -1. Oh, we've got the plus 3 on the end. Oh, that actually makes us even to a +2. And so in total, we get 2/3. Woo! All right, we did it. Now, there's a second part to this problem. So let me scroll on down and we'll get part B. Okay, so here is part B. We're now going to assume this is the same function that we had up above, right? And we're going to assume that the graph of the fourth derivative, somehow we were able to get that, right? We only had some data points for f before, but now we somehow have the graph of the fourth derivative, right? Remember, that's what this little parenthesis around the 4 in the exponent of a function means, the fourth derivative. And we're going to assume that this function, okay, oh, and of course, incidentally, right, in the previous one, it was a t, which we probably should have kept this as a t. Okay, I'll just rewrite t's everywhere there. But we're going to assume that it's given below by this function here, and we want to compute an upper bound on the absolute error of the Simpson Rule approximation. So we're interested in knowing how big an error we made in the previous problem when we got that the value, we approximated the value to be 2/3. Okay, we didn't know it was equal to 2/3. We just said it's approximately 2/3, and we want to know how much we could possibly be off by. All right, maybe we're too high, maybe we're too low. That's why we use the absolute value of the error. And so we have a rule which says that the absolute value of the error is bounded by, well, we have this fraction. And in the top, you're going to have a difference between your end points. Okay, so here we went from 2 to 8. So there we go. We're going to do 8 minus 2. And we're going to raise this to the 5th power. On the bottom, we're going to take the number 180, which just somehow magically appears when we derive this error bound, and we multiply by the 4th power of the number of intervals. Okay, so how many intervals did we have? All right, we had 6 intervals. So we're going to have the 6 intervals raised to the 4th power. And then you can see there's something missing up here. So this is what sometimes is called K or M. I like to use M. And so here we go. What is M? Where M is an upper bound. So we're trying to find an upper bound, and well, it's defined in terms of an upper bound, is an upper bound on the absolute value of the 4th derivative of f on the interval 2 to 8. So we need to know what is the biggest the absolute value of the 4th derivative can be on the interval 2 to 8. And if we just look at the data, we have no idea what that's going to be. And that's why it was so important that in this problem we were given this chart which shows us the 4th derivative of f. We don't have to compute the 4th derivative, it's just given to us, right? But in graphical form. Now we're only interested on the interval 2 to 8. So let's draw some little guidelines here between 2 and 8. And we want to know right? So we don't care about anything to the left or to the right of these guidelines. Okay, we just want to know what is the biggest this function value can be on 2 to 8, but remember we care about the absolute value. So if I'm looking for the high point, I might look over here somewhere around 3. Oops. And it looks like it's at height 3. And so I might say, oh, there you go. My max value is 3. But not so fast. Look at the low point. The low point, which occurs at about 7, is -4. And in absolute value, this is equal to 4, which is even bigger than 3. So we can see that the upper bound, right? Really the least upper bound, I could say an upper bound on the absolute value of the fourth derivative of f on the interval 2 to 8 is 4, right? Why not -4? Because we're taking the absolute value, right? This m is always going to be a non-negative number, right? Because it's an absolute value. So what that means up here is that m is going to be 4, 8 minus 2 to the 5th, that's going to be 6 to the 5th power. We divide by 180 times 6 to the 4th power, and well, what do you know? The 6's cancel. Let's see, so that's going to be 24 on top and 180 on the bottom. All right. Now, all the things I'm doing here are violating what it says not to do in the problem, but I just can't help myself, right? Oh, 12 over 90, 6 over 45, divide by 3, I get 2 over 15. Okay, there we go. So the error is bounded by 2/15. Okay, now why did I say it's violating the rules, right? Well, it says, please do not simplify your work or use a calculator. All right. So you can let Dr. Glesser do that, but don't do it if I tell you not to, all right? Why? Because it's really easy to make a mistake here, and you're wasting your time. You're on your final exam. Why would you waste your time simplifying work, especially when I said not to do it? Okay, so if you leave it right here, we're in good shape. All right, we'll see you next time.